Okay, so I'll start. So this is my title, Puzzles and Questions about Entropy and Information Loss and AdS-CFT. Now I want to scroll down, and this is also okay. So I'd like to begin by talking about the Hawking effect, the discovery of the Hawking effect in 1974, already a very long time ago, which I assume you're all to some extent familiar with. And this discovery of the Hawking effect gave rise to a number of puzzles which still are much debated and discussed today. So I want to begin by listing three puzzles. The first two, which are on this screen, refer to the situation where you have, let's say, a star. This is a kind of space-time diagram. Can you see my cursor?
Yes, as well, we can see the cursor. Yeah.
Okay, good. So, so you have a star collapsing at a certain point, a horizon. That's these green lines schematically forms, and then the star collapses to a singularity. And according to Hawking, this so you have a black hole now, and as time goes on, this black hole is radiating, Hawking radiation, represented by these wiggly yellow lines. But of course, as it radiates, it's going to lose mass, we assume, and eventually disappear, let's assume. So at the end, we're just left with radiation in empty space. Okay, and there are a number of puzzles about this. So the first is the famous so-called information loss puzzle, and different people have different ways of saying what this puzzle is, but the way I'd like to say it is that the following three assumptions, so unitary time evolution, the assumption that physical entropy increases throughout this process, and originally I think this was only made implicitly. There was an implicit assumption in early work of Hawking that at least that in physical entropy is the von Neumann entropy of the total state. And these three assumptions are in contradiction, of course, because, as we all know, von Neumann entropy is a unitary invariant, so it can't increase if time evolution is unitary. And I'd just like to remark that actually this puzzle is more general and applies to any closed system, and it's really just a special case of what one might call the second law puzzle. It's a puzzle about the second law of thermodynamics, because the second law of thermodynamics tells us that for a closed system, entropy will increase, but we have to, for any closed system, deal with the fact that these three assumptions cannot all be true at the same time. Okay. Okay, the second puzzle, which I call the firewall puzzle because of a famous paper, which I guess many of you will be slightly familiar with, at least have heard the term, which proposes a resolution of this puzzle based on a concept of a firewall. Well, I won't talk about that right now, but the puzzle is that according to monogamy, you know, the notion of monogamy from quantum information, the late photons that are emitted during this process of black hole evaporation cannot, sorry, the late photons are the ones low down here, right, cannot simultaneously purify the early photons. No, I was right the first time. Those are the late photons, and these are the early photons, which will have got further away by as time goes on than these photons. So the late photons cannot simultaneously purify the early photons and at the same time be entangled with the late black hole, which one might have assumed would be the case from the way that Hawking evaporation works. So this is the firewall puzzle. And then the third puzzle relates not to a black hole which is evaporating as in the previous picture, but you can consider, as first considered by Hawking back around 1975-76, you can consider putting a black hole in a box and letting this system get into equilibrium. So letting the black hole will be surrounded by its thermal atmosphere, and let's assume all this is contained inside a box and cannot escape, and the gravity can't escape either. Then you expect that there are equilibrium states which schematically look like this. And for these equilibrium states, there's a puzzle which some people call the thermal atmosphere puzzle. And the puzzle is this, that for such a black hole in equilibrium in a box, on the one hand, one can argue that the total entropy of this system is the same thing as just the entropy of the black hole, which is roughly speaking the entropy of the gravitational field, okay? But one can also argue, there are also arguments that it is just the entropy of the thermal atmosphere, which, okay, has a small component which consists of gravitons, but presumably is mostly made out of matter, you know, photons, neutrinos, well, if the black hole is hot enough, lots of other particles, massive particles, okay. Moreover, if you naively add those two entropies together, then you'll get the wrong answer, right? You'll get twice the correct answer, which, as we all know, is 1/4. Okay, so there are papers, I won't explain where the justification for these statements, but there are well-known reviews of black hole thermodynamics, for example, one by Don Page back around 2006, I think, and one in the journal, New Journal of Physics, one by Bob Wald in Living Reviews, okay, which explain this puzzle. But anyway, there is this puzzle. And I want to talk about different proposals that have been made to resolve these puzzles. So let me focus on three approaches that I'm aware of. So first of all, historically, Hawking, it was Hawking himself, of course, who first proposed the problem of the information loss puzzle. He called it the information loss paradox in a paper in 1976. And his resolution to the information loss puzzle was to say that the dynamics is not unitary. Physical entropy is von Neumann entropy, which I don't think he questioned that. As I said earlier, that was a sort of implicit assumption for him. And then he had this idea that you have to generalize the laws of quantum mechanics to cope with a non-unitary time evolution, and pure states evolve to mixed states according to something that he called a superscattering operator acting on density operators. Well, this is mainly of historical interest now because even Hawking later changed his mind about it, and there is now a mainstream, what I shall call the mainstream current approach. And again, there are many authors here. I won't mention any names, but well, I could point to a recent review article, for example, by Almheri et al. In Reviews of Modern Physics on this approach to the information loss puzzle, at least. So I'll abbreviate this MCA. I'll be talking about it a lot. And if I can attempt to summarize the mainstream current approach, it's that the dynamics is unitary, okay, and this is not regarded as a triviality. It's something that needs to be demonstrated, but they do demonstrate it, okay, by showing, so I'm skipping a sentence here, what they call the fine-grained entropy, or which is the same thing roughly as von Neumann entropy, for the exterior of a black hole, in the way they think about it, is argued to be zero both before stellar collapse to a black hole and after the full evaporation of that black hole, thus confirming that time evolution is unitary. Coarse grained and it's argued that you can think entropy and array component increases with time. Okay, so that's an attempt to summarize what is generally as current or modern approach, and this is still a very active field, and there are many papers and interesting results in it. But as maybe not may not be aware, but in 9 rather different information loss puzzle, rather than which I matter the entanglement hypothesis, and I'll check you're all still hearing and seeing this talk. Okay, that's reassuring, because you see, I can only somehow only see myself and can't see what you're all looking at. Okay. Okay, thank you. I'm just worried if you might not sure hear you. Okay. So my hypothesis, we must resolve the puzzle full semi-classical. Of course, we don't have a theory of full quantum gravity, but I just make some very simple and, if you like, conservative, maybe too conservative, you might think, assumptions about the nature of quantum gravity. So I assume that quantum gravity is a conventional quantum theory with a pure, I work in the Schrödinger picture, a pure state evolving under a unitary time evolution. Okay? And this, of course, entails that the von Neumann entropy of the state is always zero. It's a contact what I call the mainstream current approach, MCA. I propose to identify physical entropy with matter-gravity entanglement entropy. And then increase of entropy, and I'll discuss this in more detail later in the talk, for an initial, let's assume also that we have, for some reason, an initial state with a low degree of matter-gravity entanglement, then you would expect increase of entropy to occur if entropy is defined in this way because of interaction between matter and gravity. Okay, so I'd like next to just have two, and this is as technical as my talk will get, two slides reminding everybody.
Sorry, Bernard, there is maybe a question.
Yes, sure.
Shine Sheikh Jabari maybe wanted to ask a question.
Sure.
Yes.
Yes.
Shine, you can ask your question. Your mic is on, Shine, and you can ask your question.
Thank you.
Yeah, you have,
sorry for the,
yeah, you have
for the
access.
interruption. Okay, sorry for the interruption.
I don't. I heard you for a moment, and now I don't.
Yes, maybe the bars.
On independence. here you are clearly sort of.
It is not clear. We cannot hear you clearly.
Yeah. So can you?
The questioner perhaps type his question and then the chair could read it to me?
Yeah, it's better idea, and he can write it down. Thank you.
Thank you. Yeah.
He wrote, what about the background independence? What about the background independency, maybe?
Background independence. Well, I'm not sure what he's. I'm not sure what he's asking. Perhaps such a question is best left to the end of the talk. I guess, is he saying that this assumption that quantum gravity is a conventional quantum theory with a unitary time evolution is in contradiction with background independence? I don't see why it should be. I should add maybe that I didn't write this down, but I assume more explicitly that this is a quantum theory formulated on a Hilbert space. So you have a time evolving a pure state, which I can think of as a density operator, pure density operator. The
Bernard, he wrote, do you expect quantum gravity to respect it?
So actually, can you hear me now? I don't know if.
Yes, a little bit.
Okay.
Yes.
Okay, so I'll try to speak louder. Here you're assuming matter gravity entanglement, so you're basically assuming that we have a matter state and a gravity state, and there's a clear separation between them.
Yes,
And,
I'm assuming you've got a Hilbert space which arises as a tensor product of a gravity Hilbert space and a matter Hilbert space.
So quantum gravity theories that I'm familiar with, in particular string theory, for example, or things like that, or even loop quantum gravity, we don't have this clear separation. We don't have this tensor product structure in the Hilbert space.
Well, okay, perhaps. Well, I'm you know, I'm interested to learn these things. I wasn't aware of that. Perhaps it would help if I continue with the talk, because I'll say something about string theory a little later in the talk, and how
Sure,
I think theory relates to that. And
so,
I'd be very interested to discuss afterwards, of course, and get to the bottom of this, of what you're asking about. Shall I continue now, though?
Yes, please. Yes, Sean, please.
Yes,
Thank you.
yes. So, so let me just take a few minutes to remind everyone of things. I'm sure everybody knows this. Basic things about density operators and vector states and Hilbert spaces. So there are two ways of getting an impure density operator from pure vector states, okay? So one way is, supposing you have a Hilbert space and you have lots of vectors in that Hilbert space and lots of positive numbers which sum to 1, lambda 1, lambda 2, etc. Then if I just sum the projectors, you know, ket bra, psi I, for each of these vectors with the weights lambda I, that gives me a density operator, which we think of as the statistical mixture of the psi I with probabilities lambda I. Okay, well, that's one way of getting a density operator, one way that density operators turn up in physics. But there's another way, which is that suppose you start off with a single pure state, capital psi, let me call it, on a total Hilbert space H, which arises as the tensor product, let's say HA tensor HB, of two other Hilbert spaces, then you can take the partial trace of the projector onto psi over HB, and that will give us a density operator rho A. Okay, and you can also take do the opposite thing with A and B reversed. And in general, rho A and rho B will be impure. Okay, so they'll have a non-zero von Neumann entropy. And when we say when that is the case, we say that the total state is entangled, and we define its entanglement entropy to be the von Neumann entropy, because it turns out the von Neumann entropy of rho A in this situation is equal, you can easily prove, to the von Neumann entropy of rho B. And let me note two remarkable features about this process, which is, of course, the basic idea of entanglement, which underlines quantum information. That unlike in classical statistical mechanics, you can have a big system, okay, that's the one described by the total Hilbert space H, with zero von Neumann entropy, but this is perfectly possible for this to have subsystems, for example, HA and HB, with a big entropy, okay. And a useful piece of terminology here is that when you have such a situation, you can say that system B purifies system A and vice versa. Okay. Now, I think it's very remarkable that in this second way of getting a density operator, no probabilistic process is involved. Okay. Let me just sort of stand back here and remember, because I'm old enough to have actually attended Hawking's talk back in 1974 in November of 1974, where he announced his black hole evaporation, and it was a very spectacular announcement and made a massive impact. And there was a lot of very excited talk that, oh, so now it seems a black hole has an entropy which is an area, a quarter of an area, and you know, we used to think entropy was something that for a closed system you have to define by a process called coarse graining, but that's partly subjective and partly vague. And now here we have a physical system where the entropy is something geometrical, it's an area. And there was a lot of exciting expectation that Hawking's discovery would presage a new revolution in our understanding, our basic understanding of the notion of entropy and of thermodynamics, and would reveal new unexpected interconnections between thermodynamics and quantum theory and gravity, geometry. So, you know, in one of my motivations in this matter-gravity entanglement hypothesis was to try and think what those new, what that new theory of entropy could be like. And I must say, after that history, it's rather surprising that in the mainstream current approach, they adopt a sort of pre-Hawkingian, if I may call it that, understanding of the second law, which is still formulated in terms of coarse-grained entropy, with all the difficulties. I'll mention some of them later in more detail, that entails. Okay, so back to the talk. So it's remarkable, I think, process 2 for getting density impure states. And if there is to be a new deep understanding of entropy, you know, I would say surely the notion of entanglement entropy is likely to be involved. Well, you know, to be fair to the mainstream current approach, their entanglement entropy is involved, but maybe not in as fundamental root and branch way as one might have hoped. And as I said, that they also fall back on the notion of coarse-grained entropy at certain points in their arguments. Okay, but anyway, let me return to this basic mathematical structure, which is familiar to all of us because it's the basic mathematical structure in quantum information. Now, typically, in that structure, one identifies A with some open system and B with its environment. So this is what is done by the people who do so-called environment decoherence. And one interprets the von Neumann entropy of row A as the entropy of the open system due to entanglement with the environment. But in my matter-gravity entanglement hypothesis, I propose something slightly different. I propose to identify A with matter and B with gravity, and to take the matter-gravity entanglement entropy to be the entropy of the full closed system of matter with gravity. So this is a proposal for having a definition of entropy for a closed system by splitting, if you will, that closed system into two subcomponents, A and B, or in other words, regarding its Hilbert space as a tensor product of a Hilbert space for system A and a Hilbert space for system B, and then defining the entropy of the full closed system to be the entanglement entropy. And of course, you might ask, why this particular split? Why matter-gravity rather than some other split? Well, I have various answers, reasons behind that, but let me just mention one of them, which is that I think by taking the split to be between matter and gravity, it gives a natural resolution to the thermal atmosphere puzzle, which I mentioned above. You see, so in my picture, if I can go back to this picture, a black hole in contact with its thermal atmosphere in a box is described by a total pure state. By the way, that's very different from the way Stephen Hawking viewed this system. He thought this should be described by a total Gibbs state at the Hawking temperature, which is, so that for Hawking, the total state of this system is highly impure with a very large von Neumann entropy. But I propose that this black hole in a box with its thermal atmosphere in equilibrium is actually in a pure state, but a pure state which is entangled between matter and gravity in such a way that the partial state of matter is approximately a Gibbs state and the partial state of gravity is approximately a Gibbs state. Okay, and then if you accept that it's something like that, then it has to be, right, that the matter-gravity entanglement entropy will then equal the von Neumann entropy of each of these partial states. So the von Neumann entropy of the matter and also the von Neumann entropy of the gravity. And I think you'll agree that's a rather appealing resolution of the thermal atmosphere puzzle. Okay, well, I said this already. In contrast, for Hawking, the black hole is a total Gibbs state. Okay. Okay, well, let me now, let me now, to begin to discuss the relation, or what might be the relation. Of course, I don't know all the answers. Well, I don't even know if this is right, of course. It's a proposal. But what might be the relation between the MGEH and the MCA? Okay, so to discuss, to get some first ideas about that, let me go back to something a little bit earlier than the current activity on the information loss puzzle and look back at the counting of states calculation in string theory of black hole entropy. Now there's obviously something right about that. So I'm talking about going back to work of Strominger and Waffer from 1996. Okay, now there's obviously something right about that work because it gives spectacular agreement between certain string theoretic formulae and certain formulae in the theory of black holes that were calculated in a very different way, for example, using quantum theory and curved space-time techniques. But I think there's also something not quite right about the whole idea that an entropy can be obtained by counting states. Okay, and I think that's not what one would normally do in calculating the entropy of a closed system. So to discuss this, because it's lends itself to a pictorial presentation, let me talk not about Strominger and Waffer, but about some work which was done shortly afterwards by Horowitz and Polchinski, and this was semi-qualitative, and it was based on the 1993 ideas of Susskind, that if you take a black hole, and now, you know, for the purpose of this discussion, I follow Horowitz and Polchinski in working in pretending that string theory makes sense in 4 dimensions. Okay, it doesn't, but let's try and close our eyes to that. In some sense, Susskind taught us, if you take a black hole and you scale down the string coupling constant and scale up the string length, keeping Newton's constant, which is given by this formula, fixed in 4 dimensions, it's given by this formula in 4 dimensions, keeping that fixed, then it will become something like a long piece of string, maybe all tangled up. Okay, that's, I hope that's my understanding anyway of what Susskind and Horowitz and Polchinski say. And then Horowitz and Polchinski have this semi-qualitative understanding of how it is that you can get an entropy for the black hole which grows like energy squared, or like the mass of the black hole squared. So what they say is that the density of eigenvalues, let's call it sigma long string, and again there are oversimplifications here. In my papers, which I wrote on this in 2012, I give a slightly more sophisticated discussion, but let's oversimplifying, take that to grow exponentially. So the density of eigenvalues goes like e to the string length times e, and then what they say is that if you equate the entropy of a black hole with k times the log of sigma, long string of e, which will be this roughly k times LSE, right? The logarithm of this will roughly be the exponent LSE. K is Boltzmann's constant. If we equate that entropy at E equals m, when the string length is a constant times Gm, G being Newton's constant, this is the Horowitz-Polchinski argument, then the entropy of a black hole, you can easily see from this algebra, is a constant times k times gm squared, which, okay, doesn't give you the factor of a quarter. As far as I know, in the case of Schwarzschild black holes, far from extremal black holes, nobody has succeeded in getting that, but it shows that it goes qualitatively like a constant times m squared, which is right. So there's obviously something right about this, but there's also something wrong about this, because, I mean, well, I can give several things that I think are wrong with this calculation, but let me just say one thing here, which is very, very simple, but I think quite devastating, which is you can't take the logarithm of a dimensionful quantity, and sigma long string of e is, of course, it's not dimensionless. It has dimensions of 1 over e. Okay, and okay, you can say, well, we need to put something in the denominator here with the dimensions of e, and then everything will be fixed. But there's no hint in this story of what you should put there. Okay, and I think that this argument, there's something right in this argument, but what is right in this argument should be is what survives in this slight modification of the argument. Okay, so this, as I say, I have a number of papers back in 2012 on this, which you can sure find and read. So my proposal is that instead of talking about a black hole going to a long string, we should look at a whole black hole equilibrium state. So the black hole surrounded by its thermal atmosphere and in a box, and this goes over to a, when you scale G down and string length up, let's assume this goes over to an equilibrium state of a long string in a box in flat space-time now, surrounded by its stringy thermal atmosphere. And now you can argue that if you, and this is, well, you can read about that in 3 papers I wrote in 2012. I also wrote a review of this in 2016 called the matter-gravity entanglement hypothesis. you can argue that, so here I just state the result, that a randomly chosen pure string equilibrium state with energy close to a constant of order 1 times m, that maybe statement in brackets doesn't need to be there actually, energy close to m, will with a very high probability have an entanglement entropy between the long string and the stringy atmosphere close to a constant of order 1 times k Lm, and then basically tweaking the rest of the Horowitz-Bolchinski scaling argument, you will conclude that the black hole equilibrium state will have an entanglement entropy between the long string and the stringy atmosphere, a constant of order 1 times Boltzmann's constant times gm squared. But now, at no point do you take the attempt to take the logarithm of a dimension full quantity. So in principle, you can compute that there's no, in principle, this way of thinking about, or this slightly alternative argument fixes, if you like, that the missing constant of dimensions of energy that you would want to put in the denominator here. Okay, and so what's this got to do with matter gravity entanglement entropy? Well, I would argue that very roughly speaking, you can identify gravity with the long string. That's not quite correct because these stringy atmosphere will include stringy excitations which are gravitons, but in some sense you expect gravitons only to be a small component of the thermal atmosphere. So to some approximation, the thermal atmosphere is mostly matter, or at least when you go over under this with the inverse scaling to this story, the thermal atmosphere is mostly matter and the black hole is mostly gravity. So this entanglement entropy will be approximately the matter gravity entanglement entropy. So this is a, if you like, a hint about how perhaps these two approaches or paradigms, if you will, can coexist. Okay, so I'm not saying that this is just another way of thinking about this. There's more to it than that. The arguments in this story perhaps need tweaking and being replaced by slightly different arguments within this paradigm. But I think those slightly different arguments would have a chance of making more sense and being more satisfactory. So a few comments about the mainstream current approach then. So as I just said, perhaps a similar tweak can reconcile MCA with MGEH. However, and now I have some critical comments of what is currently done in the mainstream approach, or not so much of the results, but of their assumptions. It's not clear that MCA solves the thermal atmosphere puzzle. It's also not clear to me, maybe experts in the audience can put me right about this. It's not clear it solves the firewall puzzle, whereas I think my matter-gravity entanglement hypothesis arguably does. That's going to be discussed in the next part of the talk if I have time. May I ask how much time do I have left, by the way, please?
Thank you. 10 minutes.
10 minutes. Okay,
yes,
well, I might have to skip something, but I'll try and get to that. Okay.
Oh, okay.
So I think most of the work in the MCA focuses on just on the information loss puzzle. Let me maybe skip the next few points there, and I come back to them if there's time, but I think it's more interesting and urgent to tell you more about the matter-gravity entanglement hypothesis. So more about the version of the second law within the matter-gravity entanglement hypothesis and the resolution of the firewall puzzle. Okay, so you see, I assume that the theory of everything Hamiltonian, and I should say this doesn't actually have to be the ultimate theory of everything Hamiltonian. It's maybe the right framework for understanding thermodynamics is some version of low energy quantum gravity, where of course low energy means below the Planck mass, so that's still a very high energy as far as high energy physics is concerned. So assume that at least in low energy quantum gravity, the theory of it makes sense to talk about quantum gravity as a Hilbert space-based theory with that in a conservative conventional way with a Hamiltonian which arises in the form H gravity plus H matter plus H interaction. Okay. And as I said before, if we also assume that we have an initial state which is unentangled between matter and gravity, or if the initial entanglement is low, we expect the entanglement entropy. You would expect, right, for any such situation, you would expect the entanglement entropy to increase monotonically. I mean, okay, if your Hilbert spaces were finite dimensional, you'd expect that not to go on forever, but there to be some Poincare recurrence time. But if the number of degrees of freedom is or the number of dimensions of our Hilbert space rather is very large, or perhaps infinite, then you won't have that problem of Poincare recurrence times. So this is the matter-gravity entanglement hypothesis version of the generalized second law. It's very, very simple. Okay, but I think when people see this, they may be left dissatisfied because they still want to understand in detail how it relates to the space-time picture, right? Going back to, whoops, one more. Going back to this picture, right? They want to understand how it relates yes, sorry, I went one too far there. We still want to understand in detail how it relates to the space-time picture of black hole formation and evaporation. Well, my guess here is that as a black hole forms, somehow the entanglement occurs near the horizon, okay, in some sense. And also, because of course, even after the black hole is completely evaporated, so you've just got lots of photons and maybe gravitons, you know, moving at the speed of light outwards from where the black hole had been in empty space. If the second law of thermodynamics is right, that system should have an entropy that's even bigger than the entropy of the black hole that evaporated. So where does that entropy come from? Well, according to this hypothesis, after the full evaporation, you know, if it was the original star or black hole was large, most of the radiated particles will just be photons and gravitons. So it will be left just with mostly photons and gravitons in empty space. And I think that the way entropy arises is because those photons will be entangled with those gravitons. Now, there's an apparent difficulty here, because if you look at the old calculations by Page in 1976 of how much of different species of particles get Hawking radiated in quantum theory and curved spacetime, because gravitons have a higher spin, there's fewer of them radiated than photons, and this seems to imply that there would be insufficient gravitons emitted to purify the photons. Okay. However, you know, just as in quantum electrodynamics, an electron will be accompanied by a cloud of soft photons, right, because the electrons interact with the electromagnetic field. Well, you know, in quantum gravity, everything interacts with the gravitational field, including photons, including the electromagnetic field. So by analogy, we expect that in quantum gravity, a photon will be accompanied by a cloud of soft gravitons. So it seems to me possible, and of course there are, you know, calculations that should need to be done here, and I don't think anybody's done them. I certainly haven't, but I think it would be very interesting to try and do them, which might show that the quantum theory and curved spacetime approximation that Page worked in, you know, wasn't adequate, ignored the interaction between photons and gravitons, and maybe there's a chance that you could show that's what actually happens. Okay, and then you see, if it's true that the photons are purified by gravitons, we don't need the early photons to be purified by the late photons, because they're purified by the gravitons. So this seems to me to be a potential resolution to the firewall puzzle. Okay, well, to finish my talk, and I guess hopefully can do this in 5 minutes, let me talk a little bit more about black holes in boxes, and I'll also get to the connection with AdS-CFT, I hope, with holography, which is, after all, what this conference is supposed to be about. So let me focus on the question, what is the right space-time description of this black hole in thermal equilibrium in a box surrounded by its thermal atmosphere? Well, you might think it's this, okay? It's basically the Kruskal diagram, or rather everything to the left of this hyperbola in the right wedge of the Kruskal diagram, where that hyperbola, of course, is a region of constant Schwarzschild radius in the right wedge, which represents the wall of this box. Okay, but this already makes you feel perhaps uneasy, because then a natural question immediately arises, well, you know, how did this left wedge get there? And should we perhaps also put a hyperbola in the left wedge? Should we put a box on the other side of the Einstein-Rosen bridge? Well, nobody ever seems to address or answer this question. Okay. However, here's an interesting point, which I discuss in a paper a few years ago entitled Instability of Enclosed Horizons. And there's also another paper with Umberto Lupo with a no-go theorem about that there is no Hadamard state which is stationary on this space-time, okay, which is relevant here. But anyway, let's focus on this fact. Think about an observer who crosses the past right horizon here. As you can kind of see from this diagram, which shows what happens to the family of light rays that hit the wall of the box and bounce off it, an observer crossing the right past horizon will see an infinite amount of history in a finite amount of time, just after crossing the horizon. And this might remind you of something else in general relativity, which is the instability of the Cauchy horizon in Reisner-Nordstrom. But anyway, if you're familiar with that story or not, I think it suggests that when you switch on Newton's constant, so all this picture is maybe fine in quantum theory and curved space-time, but with matter that but where you ignore the back reaction of the matter on the geometry, and you ignore the quantum nature of the geometry, okay. But it suggests, this infinite amount of history story suggests that when you switch on Newton's constant and look in full quantum gravity, the horizons are actually unstable, and the correct space-time picture for a black hole in a box is more like this, just the right wedge with some non-classically describable region close to where you think the horizon should be. Okay. So now there is only a right wedge. Let's assume, though, that the matter in the right wedge will still be in a thermal equilibrium state, a Gibbs state at the Hawking temperature. But now there's, you know, in quantum theory and curved space-time, you assume that mixed state, thermal state of the matter in the right wedge is purified by matter in the left wedge. Okay, but now there is no left wedge, if you believe this story. But still, the total state has to be pure, according to our basic assumptions. So the only thing that could purify it is the gravity in the right wedge. Okay, so I claim or propose that a black hole in a box surrounded by its thermal atmosphere in quantum gravity is like this. You've just got a right wedge. Things are very fuzzy near where you think there should be a horizon and cannot really be described in terms of a classical space-time picture. But you've roughly got a matter field in a thermal state on the right wedge, and that's entangled with the gravity field on the right wedge, which is also in a thermal state. Okay, so this seems to me to have interesting implications for and raises interesting questions about the nature of AdS-CFT. Well, you are all experts on this subject. I'm at holography, I'm not. So I'd be really interested in your feedback on this, either in questions afterwards or privately. So the point is this, you see, you could do the same story as this black hole in a box surrounded by its thermal atmosphere for Schwarzschild AdS. Okay, so when you have a cosmological constant, that's very similar to, you know, AdS is Schwarzschild in AdS is very similar to Schwarzschild in a box in flat space-time. So likewise, we expect quantum Schwarzschild AdS to just consist of the right wedge with a non-classically describable region where you expect a horizon to be, and the total state to be pure. Okay, but in AdS-CFT, as far as I understand it, and I hope you'll correct me on this if I'm wrong, this Schwarzschild AdS bulk is believed to be due to an impure, right, thermal state for a CFT on the conformal boundary. Okay, and people normally assume that there's another conformal boundary on the other side here, but I don't think that's right. Okay, so the point is this, or one point is this: if AdS-CFT duality was a bulk to boundary bijection, this would lead to a contradiction, because it would imply that you could equate somehow a impure state, namely the Gibbs state, the thermal state of the Hawking temperature of the CFT on the conformal boundary, with a pure state in the bulk. So instead, it suggests that AdS-CFT is actually a bijection between just the matter sector, whatever that is, in the bulk, and the boundary CFT, while the gravity sector of the bulk purifies the matter sector. Okay, so if this is right, and I'd be very interested, as I say, in your feedback, it raises the question, say in a string theory understanding, which part of the bulk theory, string theory in AdS is to be identified with matter, and which part is to be identified with gravity. Well, I don't have an answer to that, but I'd be interested in your comments. Okay, I'll finish there.